Everyone, welcome to iitiansgateclasses classes. We are going to start the topic of today's discussion will be the bipolar junction transistor, right? Bipolar junction transistor, bipolar junction, transistor. Okay, transistor. So here we will discuss only the circuit part and we will talk about region of operations and we will talk about three kind of configurations, right? So as far as we know that BJT is of two kind, bipolar junction transistor has got two type. One is NPN transistor, NPN, and one is PNP transistor, right? NPN and PNP transistors, okay? So and there would be three terminal basically. It is a three terminal device, okay? It is a three terminal device, right? Terminal device. So I'm not going to talk about the physics or semiconductor physics, okay, related to bipolar junction transistor. I will be only talk about what are the various kind of configurations and how we call those configurations as common emitter, common base, and common collector. And then we will go to see that how BJT behaves like an amplifier. Okay, what is the small signal analysis of bipolar junction transistors, right? The way we discuss in case of a diode, right? So the NPN and PNP transistors. So my primary focus will be on NPN, right? So BJT, the bipolar junction transistor, has got three basic regions, right? One is emitter, and then this is base, and this is collector, right? And here you can see this terminal will be emitter terminal, this will be the base, and this will be the collector terminal, right? Okay. So I'm not going to talk about the semiconductor physics. This is covered in electronic devices, right? So let me draw the symbol, for symbol for what? Symbol for NPN transistors. Okay, symbol for NPN transistors. Okay, so the NPN transistor looks like this, right? So this is the symbol for NPN transistor. Okay, this is N. You can say this is P, this is N, right? So this, there is an arrow, right? So this is basically the base terminal, this is collector, and this is emitter terminal, right? Okay. Now let us see the configurations of bipolar junction transistor. There are three kind of configurations, right? Okay, it depends upon where we are going to apply the input. Okay, suppose this is one black box and there is emitter terminal and there is a base and there is a collector terminal, right? So we can say that if we are going to apply the input, okay, if we are going to apply the input here, we are going to apply the input where between emitter and base. Okay, if we are going to apply the input here, and if we are going to take the output between collector and base here, B out, right? So this will be so the you can see here the base terminal is common, okay, between input port. This is the input port, okay, and this is the output port, right? So you can see here the input port and output port, right? So the terminal which is common to both is the base terminal. That's why it is known as common base, right? Common base configurations. Okay, configuration. So in entire analog, we talk about four kind of amplifiers and three kind of common configurations, right? So this is common base configuration, right? Okay. Suppose we have got the base here, right? Suppose this is base and this is emitter and this is collector, right? And suppose we are applying, input between base and emitter, and we are taking output across, okay, between this and this, right? So suppose this is the input and this is output here. So again, you can see here which terminal is common. So here the emitter terminal is common, right? So that's why we call it common emitter, right? Common emitter. Okay, common emitter, right? So we will also calculate various current gains for different configurations, common emitter, common gate, and common collector, and so on and so forth, right? Okay. So now we will talk about common collector. So suppose this is your base, right? This is you can say here there is a common, and this is C, and this is B, and this is emitter. You can see. So you can see here this collector is common, okay, between the two. So this configuration is known as common collector, right? Configuration. Okay. Right. So if we want to define two ports, so how many terminals we need? We need four terminals, right? To define a two port, right? To realize a two port network, okay, to realize a two port network, okay, two port network, we need at least four terminals, right? We need four terminals, right? So you can see here, this, suppose this is a two port network. So these are the ports. This is the input port where input has to be applied, and this is the output port where output has to be taken, right? So in order to behave your bipolar junction transistor as an amplifier, we need four terminals. But unfortunately, BJT has got three terminal. BJT has got three terminal only, right? Therefore, one terminal is always common. One terminal is always common. That's why we are getting three kind of configurations. One is common emitter, common base, and common collector, right? Okay. This is just the basics I'm telling you, okay? Right. So, we'll talk about the region of operation, right? How we are supposed to solve the circuit whenever bipolar junction transistor is given, and what you have to find out basically, right? And we will also talk about the different way of biasing the bipolar junction transistors, okay? Like in case of diode, there was forward bias and reverse. Suppose there is a diode, right? So if this terminal is greater than this terminal, so that diode is in forward bias, right? And it has been replaced by its internal impedance, that is short circuit. And if the diode is having this kind of a polarity, okay, so this will be reverse biased and it will be open, right? So this was the characteristics of diode. But in case of bipolar junction transistor, so this is, suppose this is bipolar junction transistor, right? So first of all, we need to identify the terminals. So where the arrow is present, you have to always take it like emitter, this is collector, and this is, base. Okay, so if you are applying input between base and emitter, right? Okay, so this voltage will be known as VBE, right? And this will be known as VCE. This will be VCC. Okay, there will be some supply here, right? And this voltage you can see here. So these are the voltages, right? So this is a symbol of bipolar transistor, that is that is NPN transistors. So the base current here is IB, and the IC, this is collector current, and this is the IE, right? Suppose this is a node here, satisfy like this. So IE is equal to what? IE equal to I equal to I IE equal to I. Okay. So now what, when your the bipolar junction transistor, we have like that is also very important. Okay, right. Let me draw one table here, right? And let me draw this this collector, this is emitter, okay, and operates here. I'm uh, base junction, right? And depending upon emitter base junction and the collector base junction, collect line, okay, okay, and the base to, okay, so your right, there is a diode connected here, there is diode connected here, right? So in order to conduct this transistor, okay, this diode should be on, and when this diode will be on, when you will provide 0.6 voltage, right, or 0.7 voltage you can say, otherwise it will be reverse bias, right? Otherwise it will be reverse bias. So this transistor will be open, right? Reverse bias, so this transistor will be open, okay, this, so your emitter base junction is what? Your emitter base junction is basically the your reverse bias, okay, reverse bias, emitter base junction and collector base junction, and your VC, your you can base to collector voltage is also less than 0 point off. Your emitter junction should be as reason inverse, okay, reverse bias, okay, in that case the voltage will be less than 0.6, okay, this diode will not conduct, right? And your if your if your then you can start your BJT is in inverse active mode, right? This is like an amplifier, okay, region of operation, that is active region, right? So if emitter base to emitter voltage is greater than or equal to, you can say, 0.6, right? So your junction will be in forward bias, right? And if this VC VBC is less than 0.6, and this, if this junction is reverse bias, okay, if this junction is reverse bias, right, so this will be known as active region, and here the BJT will be having like an amplifier saturation. So in the examination, HAL examination question, like if your emitter base junction is forward bias and you, if your uh, will be right, so you have to keep in mind these things, right? So here the condition is if VB is greater than or equal to 0.6, so it is in forward bias, and, and if VBC, you have to make collector right, in case of saturation. So VBC is greater than 0.6, right? So it is in FD, right? So these are the operations, very important. In case of cutoff, the current will be 0, the collector current will be 0, okay? Remember these things, okay? So let me discuss one by one, okay? And I'm going to take common emitter configurations, okay, because that is going to be easy. And if we are able to do for one, you can analyze for common base and common collector as well, right? So common emitter is one very important configuration, common emitter, right? So what we will do here is we will one session. So you can see here, this is our transistor, right? And you can see here will there will be collector current, collector R, okay, R, and there is a VCC. You can connect here VCC, right, plus to minus, okay. So and here the input is connected, you can say input is connected, right? And if it is open, right, if it is open here, okay, so your diode will not get the 0.6 voltage, right? So this junction will be reverse bias. There is a diode here, you can see there is a diode here, right? There are two diodes, okay, in case of bipolar junction transistor. So this diode will be in reverse bias, this diode will be in reverse bias, okay. And between this is N, this is P, and this is N, right? So between this there is a huge resistance, okay. When your transistor is in cutoff, means that there will be huge resistance, then IC will be 0. Then the current flowing through collector terminal IC will be 0, right? In case of cutoff, remember large resistance here means that the open circuit, large resistance circuit, right? Open, okay. So you can this, suppose there is a resistance between an meter and there is a RC, okay, there is a RC and there is a VCC, that is supply, okay. So this is your collector terminal, this is the emitter terminal. If the resistance is pretty high, if the resistance is pretty high, what is the meaning of that? It will be equivalent to open circuit, right? Open circuit, open circuit, the IC equal to 0. In case of cutoff, okay, if your if your bipolar junction transistor is in cutoff, so the collector current will be 0, okay. These things are very important. And for active region, uh, your you have to keep in mind, right? So this is cutoff, it means that this guy is in reverse bias, this is in reverse bias, okay, and so on and so forth, right? Okay, now we will talk about active region, okay, region of operation. So in case of active region, RE will not be that high, RE will not be that high, because your emitter bias and your collector base junction will be reverse bias, right? So this guy is here, uh okay, and there is C, okay, this is a supply, okay, which is being supplied to the bipolar junction transistor to analyze energize, okay, right. So there is an input, okay, connected along with RB, this is V in, right. So there is a diode again, you can see there is a diode connected here, on, right. This, okay, in order to make the diode on, you need 0.6 at least. So this potential between these two should be greater, than only it will invert bias the diode again, so it will be in reverse bias if the potential is less than 0.6, right? BCE, okay, the voltage between BC, base and collector, right? So this guy will be in reverse bias, okay, and there will be a current, the resistance will be, you can change the resistance RCE, right? RCE will be varying accordingly, your IC will vary, understand? Accordingly your IC will vary as you change load, your current also varying, okay, your current is also varying, In case of active region, okay, in case of active region, you have to remember few equations, okay. In case of active region, okay, uh, keep in mind, okay, few important equations, right, to solve the numerical. Number one, IC equal to beta IB. IC equal to beta IB is valid when transistor is in active region, right? If the transistor is not in active region, then you can't use IC equal to beta IB, okay, equation, okay. Okay, IC equal to beta IB. And what is beta here? IC by IB. What is beta here? IC by IB. So what is the name of beta? Then what we can say? This is a common, okay. This is what the common emitter current gain. Okay, common emitter current gain. Why? Because you can see here, if you will calculate here IC upon IB. IC will be the output current and base will be, you the base take the output at collector, the one terminal will be common, that is known as common emitter current gain. So this beta is basically IC upon IB, okay. So this is very, very important. And second, that equation which we have got, that is IE equal to IC plus IB, right, IC plus IB. This equation is valid everywhere, right? This equation is valid for all cases, right? For all region of operations, right? Be it okay. So you know that IE equal to what? I equal to what is IC here? You can replace this IC or IB, right? You can replace this IB or IC. You can replace IC here, right? So what is IC? IC equal to beta IB. So here beta IB plus IB. So what is IE then? IE equal to beta plus 1 times IB, right? This is very, very important equation. You have to keep this in mind. And what is IB here? IB is, suppose you know IB, so you can compute IE if beta is given, right? If you know IB, you can compute IE then, right? So IE upon beta plus 1. So just I'm going to tell you this. Suppose there is a, you know, the current in the emitter terminal is known with IE. Okay, you are solving the problem and you know IE, and the beta of the transistor is given, right? That is IB will be basically what? IE by beta plus 1, right? Okay, this you have to keep in mind. The moment you know IE, you can be equal to IE beta plus 1. And these equations are equations when the transistor is in saturation region. These are very important points which I am telling you, right? Okay, right. Now, if you know the base current, right? If you know the base current, right, IB. So what is IE here? IE will be, see, when you are having emitter current, okay, current through the emitter terminal, and you are computing the current through the base terminal, right? So your emitter terminal is getting reduced by beta plus 1, right? IE upon beta plus 1 is there. Now you have got IB, so what shall be the IE? Beta plus 1 times IB, right? So this guy is increasing, right? If this is there, so beta plus 1 times IE will be there, okay? These things are very, very, very reflection. It is known as reflection, you can say, okay? If there is a RE, okay, sorry, IE, so the current is reducing, okay? and if there is a IB, the current will increase, okay, in the emitter terminal. You can also comment on the resistance as well, right? Resistance as well, because if the current is decreasing, then the resistance will increase. If the resistance is decreased, then you can say the current will increase, okay, and vice versa. Okay, this is very important, which will be useful to solve numerical problems, right? Okay. So now we will talk about saturation region, which is very, very important as well. Saturation region. Okay, saturation region. I'm not going into much detail, just I'm brushing up so that you could solve the problem, and I have to make you problem solving ready. Okay, so again the same story will be here. There will be common emitter configuration I'm taking. This is RB, and there is a supply that is, you can say that is VBB. Okay, and there is a RC, and there is a VCC, okay, to power up the bipolar junction transistor. We are using right now the single supply. Okay, so in case of saturation, this resistance, okay, this resistance will be very, short circuited, right? You can say short circuited. Okay, in case of okay, that RC RCE will be close to 0, right? Okay, so the current will flow here, that current will be okay. So when the transistor is in saturation region, your IB will be very large, remember. So this will be in forward bias, this will be in forward bias, right? And your IB will be very large here, and you can compute IC, right? Here IC will be there, and one beta will be also given for this transistor, okay? So what is the condition that, your transistor is in saturation region? How can you claim, right? How can you claim that, okay, conditions for BJT to be in saturation. Okay, what is the condition for BJT to be in saturation region? So as we know that in any bipolar junction transistor, the base current should be very small. If we are considering the common emitter transistor, okay, common emitter configuration, so the base current should be very small. Okay, why? Because if we talk about semiconductor physics, so there should be less recombination, right? There should be less recombination with the holes, right? If electron is coming from emitter is emitting electrons, okay, enormous number of electrons, so there should be less recombination in the base. That's why base is made thin, okay, so that your IE equal to IC objective can be achieved, right? Okay, if IB is small. Okay, okay, so that IB will be the active IB active, remember. So if condition for bipolar junction to be in saturation, so if your IB is greater than IB active, okay, if your IB is, the base current is greater than IB active, you can say, okay, if your IB, just I'm talking about the magnitude, okay, your IB is active greater than the IB active, okay, because in active region we want, in active region, remember, in active region we want IB to be pretty small, right? And but if that IB is greater than IB active, means this will be the saturation IB, right? So okay, so keep this in mind, keep this in mind. If this condition happens to be okay, then what will happen here is that, therefore IB is greater than, what is IB active? Basically IB active is nothing but, you know that in IB IC equal to beta IB, right? This is the relation which holds true for active region. Region of operation must be active. Your BJT should be in active region. right? And you know the condition. If your emitter base junction is forward bias and okay, then collector base junction is reverse bias, so that BJT will be in active region. Okay, so IB is greater than IB active. So what is IB active here? You can say IC upon beta active. IC upon beta active, right? From here, what we can get here is that the beta active, right? Beta active is greater than IC by IB. Okay, beta active is greater than IC by IB. Okay, so this is basically a beta forced, right? This is a beta forced, beta forced. Okay, because we are forcing that meet the base current should not be equal to 0, right? It should be and the active region, right? So you have to prove always. This is very important condition when the emitter when transistor is in SAT, so beta forced, okay, beta forced must be less than beta active, and maybe beta will be given, and you have to compute beta force and compare this, right? If this condition holds true, then you can say transistor will be in saturation region. Okay, if IB is very large, then there is there will no effect on IC, remember, right? So whatever electron will come, it will not be able to contribute because the recombination will be heavy, right, in the base region. Okay, right. So this is what I wanted to discuss. Now we will talk about the problem solving technique, for BJT, right? So the next topic is what the problem solving technique. How we have to solve the problem. What is the step problem solving? Okay, strategy, you can say strategy. Okay, for BJT. So any problem you can solve within a less amount of time. Okay, spent. So you will not make mistake as well if you will follow this. You can say a roadmap or cycle or flow chart, right? Flow. So problem solving strategy for BJT. Suppose this is a bipolar junction transistor given, right? All the node and all the node voltage and current I'm going to identify here, right? So this is your base terminal, and this is your collector terminal, and this is your emitter terminal. First of all, we are successfully identified the terminals, right? So there will be a current IB, you can say, okay, and there will be a current IE, okay, and there will be a current IC. Now let me write the potential as well. This is VBE and this is VCE, right? Okay, and this is VCB, you can say VCB, and okay, this is base and this is collector, right? These are the terminals. Okay, so and you can see if you want to find the light emitter terminals with VE, okay, the we want to find something here, so this is VC. Okay, so in the examination they will ask question like this. Okay, suppose given op amp, given bipolar junction transistor, in which region of operation it is working at, right? So you need to compute in which region of in which region your bipolar junction transistor is working, right? Okay, and for active region, as I told you, for active region you have to always check. Okay, so for active region, how you can make sure, if suppose BJT is given and you have considered that your BJT is in active region, right? So at the end of the day or at the end of the problem, what you have to calculate, right? That matters. That is going to justify whether your assumption is correct or not, right? Okay. So for NPN transistor, right? For NPN transistor, your VBE should be forward bias, your VCB should be equal to reverse bias, right? Okay. And one more important point, your VCE, the common, the collector and emitter potential between, potential between common and emitter, okay, must be greater than 0.2 volt. This is very, very important, right? If you're able to successfully identify your NPN transistor satisfy these three conditions, then your transistor will be in active region. Okay. So whenever you solve the problem, you will have to calculate all those note. You will have to calculate this your VC, you will have to calculate your VC, then only you can verify, yeah, my assumption is correct, right? So what should be the flow? Okay, what should be the flow, for calculating all these things, right? Okay. And for PNP transistor also you can write here for PNP transistors. Let me cover both in hands. Okay, transistors. So your CB will be forward bias, right? Your VBE must be reverse bias, okay? And your VEC now must be greater than 0.2. VEC, right? We'll see the problems, okay? Okay. So, right, you have to keep this in mind. So the procedure which you have to follow always is the procedure, or the flow you have to follow always is what? First of all, you need to calculate VE, the potential at emitter no, okay, terminal, and then you have to calculate IE, okay. Then you have to calculate IC, right? Then you have to calculate VC, and then check VCE, right? VCE. So this is the roadmap you have to follow always, okay. If assumption is what? If assumption is active region, okay. If assumption is active region, then you have to go for VE, then IE. So we'll take one problem and you will understand, okay. And if assumption is failed, then you have to find, saturation current. Your transistor will be in saturation, right? So let me take first one problem here, okay, very important problem. Just I'm going to take now. Okay, so let me take one problem here. Question number one, based on our discussion, find all the node voltages, right? Find all the node, okay, node voltages and branch current, right? Branch current, okay, and they have given take beta equal to 100, okay. If beta is pretty high, this common emitter current gain is pretty high, then you can neglect IB, right? Then you can neglect IB, but here they have given finite beta, okay, so we can use beta as well, right? So the question here is find all the node voltages and branch current, and they have given the circuit here, right? So let me draw the circuit for you. So this is just a transistor, okay, and they have also mentioned the value of RE this time, and this is given as 10 volt, right? Your RC is 4.7K, your RE is 3.3K, right? 3.3K, right? 3.3K. Your RE is what? 3.3. Let me erase entirely, then I will write. So your RE is basically 3.3K, right? And your base potential is known, that is 4 volt, right? Okay. And you can assume that the potential here is VB is given as 0.7, right? Okay, so now let us compute everything, okay, all the node potential and everything, right? So as far as I told you that first of all you need to calculate VE, so you can calculate VE, right? So it is a NPN transistor, right? So the way you move on the transistor, right? The way you move on the transistor, you have to either add the potential or subtract the potential, right? Suppose you are moving downward, right, from plus to minus, and it is 0.7, okay, this is positive potential, that is 4 volt, therefore your transistor is on, okay, because this diode demands 0.7, this junction demands at least 0.7 voltage to make the transistor conduct, right? So it is a forward bias, okay, so this 4 volt is there, right? And there is no base resistance, right? So the moment you will come down from plus to minus, remember, whenever you come down, okay, so this is 4 volt and there is a 0.7, okay, and somebody wants what is the value of VA here, right? So you're coming down. If you're coming down, so your potential will decrease. So how you're coming down? You're coming down from plus to minus, okay? So if you're coming down, your potential will decrease. So 4 here it is, and this is 0.7. So your VE will be what? 3.3 volt, okay? 3.3 volt. The moment you got VE, so you can compute IE here, okay? What is IE then? IE will be 3.3 upon 3.3 kilo, means 1 milliampere. IE, emitter current you will get, right? Now you can compute, okay, what? Now you can compute IB and IC, right? If you know IE, if you know IE, that is 1 milliampere. What is IB? IB, as I told you, that it will be decreased. IE will be decreased by beta plus 1, right? So I is 1 milliampere and beta plus 1 is what? That is 100 plus 1. You can say that this is going to be, you can compute here, right? Approximately your IB will be what? Your IB. Either you want to calculate IB or don't calculate IB, no problem, right? Because IB is not going to help you to satisfy whether the transistor is in active region, right? So I, and you can calculate IB if in the question they have asked, okay, by the from this, okay. But what I would suggest here is that directly compute IC, right? As I told you in the flow. See, first of all, I calculated this guy, then we calculated this. Now we need to calculate this. How can we compute that from IE? Okay, from IE, how can we compute IE, right? So as we know that IC equal to what? IC equal to IB plus IE, right? IB plus IE, okay? And here beta is given, right? Sorry, here IB is given. So IB here, I will be IE upon beta plus 1 plus IE, right? Wait, the mistake is here. Wait 1 minute. Right, the total current IC plus IV, right? Total current IC plus I will be equal to IE, right? This is the node equation, correct? Okay. So now yes, in place of this IB, you can place this guy, that is IE upon beta plus 1 equal to IE, right? Just I'm deriving the formula for you, okay? Now what you can do here is that you can take this guy that side, okay? So this is IC because you want IC from IE. So IE is common, okay? So 1, 1 minus 1 by beta plus 1, right? So if you will compute this guy, so what is this? IC upon IE equal to what? beta plus 1 minus 1, that is beta by beta plus 1, right? Okay, so we know that IC upon R when the base is what? Base is common. Okay, when base is common, it gives you what the relation beta by beta plus 1 base current gain, but common is current gain. Okay, common base current gain. So these are the quantity you need to and gain. Beta is known as current gain. Okay, current gain. Please take care of this. Okay. So if you're coming down, right? If you're coming down, so you got that 3, okay, 3.3. Then you have got I was 1. You can compute IC equal to beta by beta plus 1 times 1 milliampere. Okay, if beta is pretty high, then you can say IC equal to IE, that is 1 milliampere only, right? Pretty high, or it is not given in the question. Then IC equal to IE, right? Here IB is equal to 0, remember. But here they have given some beta, so we on 101 into 1 milliampere. Okay, so from here, in fact, so your IC will be equal to 0.9909. You can see here it is very close to you know, IE, right? Now what you can compute circuit, this, right? So you know now this guy, this is VC, you know, that is 0. Okay, after solving 9, okay, 9909, right? Or it's also valid for what? For active, right? Only valid for activity. So now you have got VC, so you can compute. Sorry, you have got what? You have got IC, not this VC. Okay, I'm very sorry for that. Okay, so you have got what? IC. Now you can compute VC. What is VC here? You are again coming down from plus to minus, right? And the drop across this will, so 10 minus drop across this 4.7 will give you VC. So let me write here. Whenever you come down from plus to minus, you have to subtract, right? Remember, you have to subtract. So your VC will be equal to what? Your VC will be equal to 10 minus, you know, IC, RC, okay, IC and RC. So 10 minus IC is 0.9909 milli and kilo cancel, RC is 4.7, right? So your VC will be coming out to be what? Your VC is coming out to be 5 point, 346. Okay, understand? So now you can compute what you have got. VC, you have got VE, and VE was 3.3. So you can compute VCE, VC minus VE, that is 5.346 minus 0.3 okay, or sorry, 3.33, right? 3.33. So you can say that you are getting VCE as 2.046, okay, which is greater than 0, right? And it is also greater than, you can say this guy is greater than 0.2, right? So my assumption, if I made the assumption that transistor is in active region, so by looking at these conditions, you can say that thus the transistor region is in active region. Okay, remember. So this was first question. Okay, so they will not ask all the node voltages and current. They will ask some voltage, or they can ask you to identify whether the transistor is in cutoff, linear, or saturation. So you have to justify. So very important note I'm giving you. Or maximum time you will find in the gate or any PSU or HL examination. If beta is pretty high, if beta is in the question, they will mention beta is pretty high or alpha is close to 1, right? Then consider IB is equal to what? IB equal to 0, right? And so from here IC will be equal to IE. This is the perfect approximation you can take, right? If beta is pretty high, suppose beta is given as 200, so you can consider beta, is high. Don't put beta in the equations and makes the life tough. Okay, right? So let me take example number 2 again, and compute all the node, okay, all the potentials and currents and everything, okay, and check whether transistor is in active or saturation, right? So let me draw the circuit here. So you will see here something great happening, right? So this is the part what we are doing here is, this is a DC analysis basically I'm doing, okay? When we will discuss amplifiers, so there we will do, we will go for a small signal analysis, okay? So before that we would require to find the stable points, or we can say we would require to find the IC current, okay, the collector current, you can say. This is +6. Okay, and this guy is given as 4.7K only, and the supply is given as 10 volt plus 10 volt, right? And this RE is given as 4.3K, right? So first of all, what you have to find out here is that you have to find out, first of all, you can write here, assume that transistor is in active region. Okay, the moment you assume, you have to prove it. Okay, if if it is not in active region, then you have to compute all the currents and voltages for saturation region, right? Okay, that is 6 volt, right? This is 6 volt. Suppose it is having 0.7 volt, right? And the beta you can take it 100 only, right? You can take beta here as that. Beta is what? The active beta. So how can you compute VE? Simple trick I have told you, that if you're walking from plus to minus, and if you're coming down, okay, because these polarity you can't change as far as this is NPN transistor, right? So this is very important observations, okay. Okay, you will not need to remember the formulas, okay, because already in different subjects you need to carry many formulas. Okay, if those subjects are not taught properly, and you haven't been told how to keep the formula in track, okay, the way I'm telling you right now. So uh, uh, here you need to understand, if we go down, okay, 6, and we are going down 0.7, so the value will be here 5.3. Okay, the value will be 5.3 volt. Now you can compute current IE. Let me write here separately. Your V is what? Your V on the circuit itself you can solve, okay, on the circuit itself. But let me write everything step by step, right? So 5.3 volt you have got here. Right now, this is the first step, right? Second step will be what? Second step you have to compute IE. IE will be equal to what? VE by RE, the resistance at emitter terminal. So this case is also known as emitter degeneration. Remember, whenever the resistance is present in the emitter, that condition known as emitter degeneration. I'm not talking those things right now. Just I'm talking about how to find node voltage in at any node of the transistor, bipolar junction transistor, and how to determine the current, okay, the emitter current, the collector current, and so on, right? Because if beta is pretty high, then you can neglect base current as well, right? So VV upon RE, that VV we have got is 5.3 and this is 4.3, right? So if we are going to solve this, so this will give you the value as 1.2325 milliampere, right? Okay. So my I we have got here, I is this. Okay, based on our assumption that our transistor is in saturation. Sorry, not saturation, it is in active region. Third step. Okay, so the moment you found third step, that is second step, that is I, now you can calculate IC. And what is IC? We know that already we have computed the formula, that is beta by beta plus 1 IE. So the moment you will put beta 100 by 101 into 1.2325 milliampere, right? 2325 milliampere, remember. Okay, this is 3, this is 2. Okay, so this is what we have got. So the IC will be what? IC will be very close to your IE only, because beta is finite here. If the beta is pretty high, then IC will be equal to emitter current, right? That is 1.2203 milliampere. Okay, so the moment you got IC, right, now what you have to find? You have to find fourth step, that is VC. VC will be equal to what? VCC minus IC times RC. That is VCC is 10 minus IC into RC. RC is in kilo and IC in milli. Milli kilo cancels. So you can write IC, that is 1.2203. Let me raise this again. 10 minus 1.2203, right, into 4.7, right? So what you will get here is that VC you are getting, as if you will compute this, so the 4.26 volt you are getting VC. Now what you can do here is that the fifth step you have to check what is the value of VCE. VC is 4.26 minus, and VE was what? 5.3. Right. Let me show you here the VE, this guy. Okay, VE was 5.3. So if you will subtract this, so this guy will give you the value less than 0, right? It means that your assumption is wrong. Therefore, you can write here, therefore transistor is not in active region. Okay, and assumption is wrong. Okay, assumption is wrong. Understand? So whenever you go down, you have to subtract and you have to compute VC, and now VC is coming out to be negative. You can say transistor is not in active region, right? So what now next, what will be the next step? So definitely your transistor will be in saturation. How? Because transistor is not in cutoff, not in active region, then transistor will be in saturation. So now you can let here the VCE, though they will give you VCE value, but if it is not given, right, if it is not given, then what will happen? VC equal to 0.2 volt you can choose, right? And you can find beta, let this, and find beta forced, right? Beta forced. So now what will happen here is that your V will be same. Your V will be, now start from the first step again. The V will be 6 minus point something, what was 0.7, right? So this will be equal to 5.3 volt. That is okay. Second step will be VC is given, right? VC already we have considered that zero point 0.2 will be there, at least 0.2. Okay. So from here you can find VC as well, because the potential you need is, so VC minus VE is equal to 0.2, right? From here VC equal to what? 0.2 plus VE, that is 5.5. Okay, you will get 5.5, okay, 5.5, right? Okay, and if there is a transistor, so you don't have to worry about anything. See, if the values is 0.2 here and this is 5, so if you're going up, okay, if you're going up from minus to plus, okay, if you're going up from minus to plus, okay, so you can add that, you can add, because that will increase. So the moment you will go up, so here the increased value will be there. So the VC will be 5.5 now in case of saturation, 5.5 volt, right? The moment you have got VC, right, the moment you have got VC, what you can find out now, you can find out IC. What is IC then? Thus IC will be equal to VCC minus VC by RC. See, if the transistor is in saturation, if the transistor is in saturation, okay, don't use don't use IC equal to beta IV, right? Very, very important. So you will have to use this concept, right, the way we are solving. So your IC will be what now? Your IC will be equal to VC is 10 minus VCC is 10, okay, minus 5.5. Already we have computed upon RC was given as 4.7 milli kilo, sorry. So it will give you milliampere, that is 0.957 milliampere. So this is the saturation current you have got, IC sat you can say, okay. And IB, how can you find IB now? If you have got IE and IC, okay. So as we know that IE equal to what? IE you can find out from VE by RE. So your this will be same only, right? That was 5.3 upon 4.3, right? Okay, that is 1.2325, right, milliampere. And if they are asking, you can use the equation, that is IE equal to IC plus IB. So from here we want IB because we want to find beta forced. Okay, we want to find beta force, and beta force should be equal to should be less than beta active. Okay, for saturation. Okay, so a smart way of solving the question is, in the examination they will give you the value of resistance, the value of potential across each junction in such a way that you will not require any calculator, right? I'm taking the value slightly different, right? Otherwise you will get 1 milliampere, then you can go ahead without using calculator, you can solve. Okay, so your IB will be equal to what? IB will be equal to IE minus IC. From here you can compute IB, right? From here you can compute IB. IB you will get here, it is 0.275 milliampere. Okay, so you have got IC, you have got IB. IC you have got is 0.957 milliampere, and IB you have got is, you can see IB is in milli range, right? Otherwise if the transistor is in active region, so your IB can be written in micro. Okay, it will be very less. Okay, so here you can see IB is comparable, right? 0.275 milliampere, right? Means here IB is greater than IB active, right? So that's why it is in saturation. So now therefore you can compute beta force. Okay, beta forced. Okay, so IC upon IB, that is 0.957 upon that milliampere gets cancelled, 275. So your IC upon IB will be equal to what? 3473, right? Which is really less than the beta active, because beta active is given as 100. Okay, therefore the transistor is in, therefore transistor is in saturation region. Okay, so please whenever in the examination you will find question from this, so you can solve. Okay, don't solving blindly, make assumption, prove it, get any question you will get, you can solve all questions very easily. Let us take third problem. The third problem here says that suppose this kind of a situation is given. Okay, here this is the situation given, right? This is VE and this is VC. Okay, and this is VCC, that is 10 volt, and this is 4.7, right? 4.7 K. Your RC is given, and RE is what? 3.3. What this time I have done is, I have let me raise this and write properly. 3.3 K. So what this time I have done here is, the base is grounded. If the base is grounded, you can't get 0.7 here. Okay, in order to have the 0.7 voltage here, you need some voltage, right? So what you can say here is that the diode connected between these two terminal, let me raise this 0.7 here. Diode connected between these two terminals, right here. So if it is grounded and if there is a diode, okay, So, at least this diode is not ideal diode, right? It demands 0.7 to turn it on, right? So this entire configuration, the BJT will not be inactive or saturation, it will be in cutoff region, right? Because, okay, so this guy will be off, understand? So therefore the transistor is in cutoff. And if transistor is in cutoff, so your VE will be 0, your IE will be 0, everything will be 0, right? Your IC will be 0, okay, and your VC will be equal to VCC. So in this manner you can compute this, okay. So as I told you that if the beta is pretty high, right? If beta is pretty high, neglect IB, please, and you can solve any question very quickly, right? Okay. So let me take one big problem, right, so that you could realize this. Suppose this kind of configurations are given, right? Let me draw this so confidently you can solve. Okay, the voltage divider biasing is given, right? Uh, with this kind of situation, you have to calculate output voltage. Okay, so this there is a transistor associated NPN and PNP both, right? And once we will solve this problem, just you have to draw with me first. So you will see how quickly we can get the answer for this question, right? And the same, this kind of a value will be given in the examination like HAL or in the gate examination particularly, because you will not be having much time to use calculator and solve big okay, so online calculator will be involved. So the calculations are very easy if you are able to understand the concept, right? Okay, again the same, this is like this, okay. So the values here is given, this is 1k, 1k, this guy is 1k here, okay, this is 4k, okay, this is basically 3.3k, right? This is 4k again, okay? And this is 7k, and this is 3k, right? So the other resistances given, and this is 2.3k, okay. In such a manner they have given, you will understand 2k, 1.3k here, this guy is given as 3k, okay, this is 5k, you can see, and this is 4k, right? So what you have to find out, you have to find this V naught, okay? This V naught you have to find, and the potential between this base to emitter is 0.7 always, and the supply is given as one single supply. One single supply is given here, is that is 10, okay, 10 volt. So now they did not mention about beta. Suppose beta is also given, so beta will be pretty high. In this question you can assume alpha equal to 1, okay, you can say alpha equal to 1 or beta is high. beta is high means you can consider infinite, right? So if beta is high, IB will be 0. So this is 10 volt, right? This guy is 0. So 7K and 3K will means series. Okay. So you can compute the potential at this point. So 10 is here. Total 10 volt will be here. So divider rule. Okay. 10 into 3 upon 10, right? So we can say there will be 3 volt. Okay. 3 volt will be here, and 3 volt we are going down 0.7, right? So this potential will be 2.3 volt, right? The current will be here what? 2.3 upon 2.3 kilo means 1 milliampere current. And the same current, see, if the base current is 0, right? So the IC will be equal to IB. Sorry, IC equal to IE, right? This is very important relation I told you. So the current will be same here. So this is 1 milliampere. And the voltage drop here is plus to minus, that is 4. This kilo into a milli get cancelled, right? So the potential here is 6 volt, because 10 is the VCC here, 10 volt, right? And the 10 minus 4, that is 6 here, right? Okay. Now minus to plus, you have to go up here, right? You have to go up 0.7. You have to go up 0.7, and there is a 6 volt. Okay, there is a 6 volt and you have to go up 0.7, right? So this will be what the potential at this point will be, a 6.7 volt, right? Because you're going up, and how you're moving up? From minus to plus. If you're moving up from plus to minus, means you're going down only, right? But you are moving up from minus to plus, so you can say that the voltage will be increasing. So you can say 6.7, right? So once you will divide 6.7 and okay, and 10 minus, so the you can find the current here, right? What will be the current here at this point? The current will be 10 minus 6.7 upon 3.3K, right? That is 1 milliampere only. Okay, that is 1 milliampere. Okay, the current will be 1 milliampere. The same current will flow here, 1 milliampere. The potential here is 2 volt now, because 1 milliampere into 2 milliampere. Okay, because the base current is neglected. So this 2 will be coming down here, that is 0.7. So the value will be 1.3 volt, and the 1.3 volt means this again the current is 1 milliampere. 1 milliampere current will be flowing here. The potential drop here is 6 volt, right? Because 10 minus 4, that is 6. Now you are going down 0.7. Okay, so it will be 5.3 volt. Again you are going down 0.7. Okay, so here you will get 5.3 minus 4, 0.7, that is 4.6 volt, and again you are going down 0.7, right? So you will get V naught. So V naught will be equal to what? 3.9 volt. Okay, so this question looks horrible, but you are able to compute everything on the screen itself, right? On the screen itself. So if you will follow everything, so you will get the answer quickly, right? Okay, so you need not to use various pages to solve this kind of a question, because the concept here we have applied is what? If the beta is pretty high, the beta is pretty high, then the beta is pretty high, then what? Then the IB is 0. I hope this is clear for everyone. Now let's talk about biasing of a BJT. What is the purpose of biasing, right? What is the purpose of biasing? So biasing of BJT. Why we bias the transistor? What is the reason? Okay, so you will come to know that your collector current is very sensitive to the beta parameter, right? That beta, beta of the transistor, right, which is known as the common emitter current gain, right? uh, if beta varies, your IC varies, right? So you can't get the constant current. Actually, our main objective will be to make the transistor uh, current constant, okay, constant to all parameter variations, right? So it should be constant, okay. Okay. So biasing of BJT, the main purpose of biasing is what? The purpose of biasing is to switch on the BJT to work in active region. Remember, right here, the purpose of biasing on to work in the purpose of biasing is to such that this important line, such that such that DC collector current remain constant, okay, remain constant independent of beta temperature and load variations. Independent of, so to make the collector DC collector current independent of beta, independent of temperature, right, independent of beta temperature. Okay, if IC is changing, okay, because of, IC can change because of temperature as well, because if the temperature changes, the potential across BBE, right, base to emitter junction changes, right? So that problem is also known as the drift problem in bipolar junction transistor. So nowadays in the gate examination, you might have seen that no questions are being asked from bipolar junction transistor. Why? Because this beta, the bad parameter beta, makes the transistor very bad, okay. So nowadays they are not asking question from bipolar junction transistor because beta is quite sensitive, okay guy, and temperature and load variation, right? So this is the purpose you have to keep in mind, okay. Sometimes they will ask questions based on purpose as well, right? In the options they might mention, okay. Here is the situation. You can keep in mind that IC will be here, right? And if there is a load, so your IC should be independent of this load, okay. You change the load but IC should be constant, right? You change the load but IC should be constant. We want constant current source, basically constant current source. I discussed in case of in case of op amp as well, when we were trying to design integrator circuit. So IC should be independent, right? So IC should not be the function of what? Beta, temperature and load, okay. And IC should also not be the function of the beta, you can say, or VBE, because if the temperature changes, VBE changes, okay. or VCE. Okay, IC should be independent of everything. Okay, we have to find the biasing technique which can make IC independent of everything, right? Okay, so if beta changes, if beta changes, right? If beta changes, IC changes. How? IC changes, right? How? Because we know that IC equal to beta IB. Okay, and because of temperature, right? Because of this is first. Because of temperature, your VB changes per degree centigrade, right? Your VB will vary minus 2.5 milli per millivolt per centigrade, right? It will vary centigrade per degree centigrade, minus 2.5 voltage will be decreased. If the temperature changes, VB will change, and this will change IB. Okay, remember, if temp changes, VB changes. This will change IB, and if IB will change, then IC will change. So we can't get the constant current. Understand? Okay. This is very important. In case of load variation, what will happen? Suppose there is a R, okay, and this is the transistor, right? And this RC is varying. This RC load, okay, is varying from 1K to 5K, okay, and there is a VCC. If this RC is changing, right? So the constant current, we want 1 milliampere constant current, right? We want 1 milliampere constant current. So if we will draw the IC versus VC characteristic, right? VC characteristics. So initially we want this, right? We want we want this kind of a IC versus VC characteristics. But because of this load variation, okay, because of this load, your IC will start varying like this. Okay, understand? So this is known as, this is happening because of early effect. Early effect. Okay, so you can extrapolate this backward, and you can also find the early voltage, okay, from the IV characteristics. IV early voltage VA. So remember, whenever collector current changes because of this load RC, so in physics, semiconductor physics, you can say there is an early effect in bipolar junction transistor. Okay, so here you can see this is the constant current, but this current start varying. So there is a slope in IC and VC. If there is a slope, then there will be finite resistance. Okay, finite resistance. This is very important concept. So if RC changes, VC changes. Understand? If RC changes, VC changes. Then IC will change. Okay. Please keep this in mind. So in order to get rid of all this problem, we should make constant current source, right? So here you can keep in mind, in order to get rid of these things. In order to get rid of these things, we must build, okay, we must build constant current source, okay. That's why nowadays loads are also being used as an active load. So we do not talk about bipolar junction transistor because of beta and temperature variations. Your IC gets fluctuated. So we don't use bipolar junction transistor. Most of the time nowadays CMOS technology is being used, and there are various advantages because of that. Okay. In fact, in the gate examination also you might have seen, if you have given, so they are not asking any question from bipolar junction transistor. They are asking only from questions from op amps and questions from MOSFETs, right? Okay. So let me talk about first kind of biasing technique. First is the fixed bias, right? Fixed bias or fixed base bias. We have to fix base, fixed base bias. Okay. So let me fix it, right? There is a common emitter only, and this is our, we are going to use single supply now. Okay, so this is a single supply, that is VCC plus VCC, and we will fix it, right? We will take we will give the supply from the single supply only using one resistance, right? Then now this IB is fixed because VC and this guy is fixed, right? 0.7 volt. If there is no temperature variation, if there is a temperature variation, this 0.7 will also vary. Understand? So you can say that, forget about this 0.7, just write VBE. Okay, and this is RB. So you can write here, you can compute what, you can compute IB here. So you can write IB directly. So IB will be equal to VCC minus VBE by RB. Okay. Okay, you can apply one KVL if you are not able to write like me. So you don't have to remember, right? So you know this potential, divided by this. Okay. So with the help of this, if this, you have to consider what, you have to consider VB is constant, right? If this guy is constant, you have to consider VB is constant, RB is constant. Okay, then IB will be constant. IB will be constant, right? So what is IC then? IC will equal to beta times B. If it's constant, this is constant, right? But this guy is a culprit. Okay. Okay. So IC equal to what? Beta IB. Understand? So IC equal to beta times of IB. IB is VCC minus VBE by RB. Okay. So beta changes from 50. If suppose beta changes from 50 to 250. Okay. For the different remember, for the different situations, okay, for the different specimens, okay, of the given transistor type, uh, so understand, so you have to keep this in mind. If the beta is changing, right, if this guy is changing, okay, if this is changing, then IC will be changing. Understand? If IC will be changing, then you know you can't get the constant current source, right? So this beta makes the transistor very bad. So remember one thing, despite transistor is very bad, but in your HAL exams, in ISRO, in PSU's exams, right? In IES, they ask questions from bipolar junction and transistor because these are the basics, right? But in gate examination, as you know that gate examination is conducted for higher studies, so you will go into the IIT or ISC and go into the industry. So there you will not find bipolar junction part of transistors of transistor, right? You will always work on MOS, metal oxide semiconductor, or CMOS complementary. Okay, right. So if this is changing, then IC will be changing. Okay, right. So this circuit, fixed bias circuit, like I have taken here, is that it is grounded and there is no RE. Okay, there is no RE. Okay, so fixed bias circuit can be with RE or without RE, right? Without RE, IC, you have to use IC equal to beta IB, right? With without RE, right? Without emitter resistance. Without RE and with RE. With RE means what? Emitter is degenerated. It is known as emitter degeneration, right? Emitter degeneration. If RE is given, then you have to be very conscious, right? You will have to be very conscious. So your IB will be different, right? Your IB will be different then. Okay. Your IB will be what? Your IB will be VCC minus VBE upon RB. Okay. RB plus. Okay. Uh, RB plus beta plus 1 times RE. Okay. Beta plus 1 times RE. Right. This is the situation. Okay. Because yes, if there is a IB, then IE will be equal to what? Beta plus 1 times IB into, times RE. Yes, this is correct. Okay. So IB, RB plus beta plus 1 RE, and this is the equation, right? With RE. And without RE, this beta plus 1 times RE will not be present. Understand? Right? So without RE, your IC equal to beta equal to IB, beta into IB, where IB is constant, you can say, right? Constant. So your IC is this, which is direct dependent, which is directly depending upon the beta. Okay, beta, right? Yes. So let me draw the circuit with RE. Okay, circuit with RE and compute IE. Okay, IE, and let us find the condition by which we can make IC or IE independent of beta, right? So the circuit with RE I'm drawing, and see how I'm writing direct without applying any KVL or kind of. Okay, RC, this is RE, right? That's VCC, and this is RB, right? This is IB. Okay, and here it is IE. If this is IB, then what is IE, right? I will be beta plus 1 times IB. Okay, beta plus 1 times IB, and remember always, right? And if this is IE, then IB equal to what? IB will be equal to IE upon beta plus 1, right? So if I apply 1 KVL here, right, and the voltage across this is VBE. So we can write directly IE, because the IE here it is flowing IE by beta plus 1, here IE, right? So the IE equal to VCC minus VBE upon IE times RE means RE plus this resistance, this RB will come this side, okay? See, this RB will come this side, okay? So what will happen? RB by beta plus 1. If this RE will go that side, then this RE will be into beta plus 1, right? So there is a reflection of resistances. If this RE, okay, I will write, okay, separately. I will explain that trick, okay? You have to keep in mind. If you know IE, so you can compute IE here. You can compute IB here, right? I by beta plus 1, because your current will get reduced, okay? So here you can see IC equal to VCC minus VBE upon RE plus RB by beta plus 1, okay? So what condition we need to consider, okay? What condition we need to consider so that IE is independent of beta, okay? What is the choice here? What is the choice, right? So if RE is far greater than RB by beta plus 1, right? Choice is what? If RE is far greater than RB by beta plus 1, right? Then IE, okay, then IE equal to what? I will be equal to VCC minus VBE upon RE only, right? Understand? And which is equal to IC as well, which is equal to IC. Because now it is not depending upon beta, so you can say this is IC equal to IE, right? So, but you will have to choose in case of circuit with RE, in case of degeneration, emitter degeneration, okay, fixed bias, okay, circuit with emitter degeneration, emitter degeneration or RE, your choice, okay, choose, right? Choose RE is far greater than RB by beta plus 1, always. Design problem, okay? This condition can also be asked in the examinations, right? So your IC DC equal to IE approximately equal to what? VCC minus VBE by RB. Okay, sorry, RE. Understand? RE. So this RE is also a kind of stabilizing resistor, right? This will stabilize your IDC. See, now your IC is not, your IC is independent of beta. IC is independent of beta, independent of beta. Understand? So this is very important, because this, if you keep this design constant, right, then life is very easy. Okay. So that was the fixed bias circuit along with RE, and the very versatile which we always use is the voltage divider biasing, right? Voltage divider, instead of fixing base we can go for voltage divider biasing. Good way of biasing, okay? This is the good way of biasing, right? Or it is also known as self bias circuit, self bias, okay? Or it is also known as universal, you can say universal bias, okay? Everywhere you will find in case of BJT or MOSFET, anywhere you will see, you know, this voltage divider biasing, okay? So what is voltage divider biasing? Basically like load will be given, okay, load is given here and the transistor. Now I'll take RE as well along with that RE, because RE will not harm here, right? RE, and you can take, you can power up your transistor and bias it, right, along with these two resistances. In future, you will find that these two resistances are neglected also whenever we try to find the gain of the transistors. Okay, plus VCC. These resistors are used for the biasing purpose. Okay, these R1 and R2 are used for biasing purpose. Okay, this is RC, right? So if beta is high, then it is very easy, right? But if beta is not high, right? Suppose beta is not high and the question is like this. Okay, then how to find RE? Okay. I can write directly, but I will tell you how to find, how to solve this kind of a circuit, right? This is R1, this is R2, and the supply is VCC, and this is RC, right? Okay. The beta, okay. Though in the question beta will be infinite, okay, high. So directly you can use division and you can find these potentials, right? Okay. But if the beta is not high, means IB will be there, right? IB will be there, okay. So what you can do, you can see from here and theorize it, right? Theorize. What we will do here is we will make the transistor as it is. This RE, there is a load, that is RC and plus VCC. Now what we have to calculate RTH, and here you have to calculate VTH, because you can see from here. So if you are seeing from here and forget about this, just open it. So R1 and R2 are in series. So by voltage division, VTH will be VCC R1 by R1 plus R2. And if you are looking from here, so the current flowing like this. So R1 and R2 means R1 parallel R2, right? Now you can find easily IE here. IE. Okay. What is IE? This is what the VBE, right? So I can write directly, right? Because IE will be VTH minus this VBE upon RE plus RTH by beta plus 1, right? So let me write here the IE by inspection. By inspection, right? You should be able to write IE, okay, without applying KVL, KCL, right? So that you can get the answer very quickly, okay? And understand how I'm writing all these things. The trick, what trick I'm applying, right? So I will explain that trick as well. Hmm? So IE can be written as VTH minus VBE upon RE plus RTH by beta plus 1, where you know that the VTH is basically VCC R1 by R1 plus R2. I think this is R1, right? This is R2, sorry. Let me erase this. Uh, yeah, it's okay. This is R2 and this is R1, you can say. So everything will be correct, right? No problem. Yeah. Okay. And this RTS is R1 parallel R2. So now you want I, okay, to make free from beta. So what you will have to do, either keep beta high, or you can say choose, okay, or choose what, RE far greater than RTH by beta plus 1. Okay. So your IC will be approximately equal to IE VCC minus VBE by RE. Okay. Independent of beta, but still your IC is depending upon VBE. Okay, so these are drift problems. So in future you will see that there are circuits, where BJT and op amp, okay, where BJT and op amp we combine, okay, in order to avoid the drift problem, right? Drift problem in the BJT. So this is very important, right? This is the self bias circuit, and always keep in mind, if beta is pretty high, then solving questions are very easy. Okay, so you can note here is that designing a current source with op amp, right? Remember, designing a current source, okay, with op amp. Okay, this is our need, right? Because IC equal to what? VCC, sorry, VTH minus VBE by RE. So after all, this guy is dependent upon VB, right? So there is a drift problem.